Hello everyone. So today we are going to discuss about atmospheric turbulence. In the last class we had studied about how the laser beam is affected by the path loss and also how it is affected by the pointing error loss. So today we will understand about atmospheric turbulence, what is the effect laser beam will have depending upon what kind of turbulence you have in the atmosphere. So if you model the system, the output is Y is equal to, say, responsivity and channel state, the input information, plus the noise, which can be assumed to be AWGN. Now this channel state H will have actually three components. One because of the path loss, which let us call that as HI. The other could be because of the pointing error loss, let us call that HP. The third part is because of the turbulence, let us write as HA, atmospheric turbulence. So we have studied about HI in the previous class. Also we had some discussion around HP or about the loss because of the pointing error. So today we are going to discuss the atmospheric turbulence part. So what actually happens in atmospheric turbulence when you have warmer air in the ground? It is less dense. It goes up and mixes with the cold air surrounding it. And because of this mixing, there are certain inhomogeneities which are formed in the atmosphere, and they act as a refractive prisms. And these inhomogeneities are of different orders, small inhomogeneities or large inhomogeneities, and actually they are called as eddies. So they are of different size, they have different temperature, they may be traveling at different velocity, they may have different refractive index. So when a laser beam passes through these eddies or different sizes of turbulence which is there in the environment, it suffers phase and amplitude fluctuation. Now if you are dealing with IMDD systems, that is intensity modulation direct detection system, in that case we will be concerned only with the fluctuation which is happening in the amplitude, because this modulation scheme basically depends on the amplitude of the signal or the electric field or the intensity of the signal. And if you are dealing with coherent communication, then I should be worried about both amplitude as well as phase fluctuation. So atmosphere is basically consists of, you can call this as a viscous fluid. And this viscous fluid, the flow is, there are two types of flow. One is laminar, the other one is turbulent. The laminar flow is something like this, and turbulent, it is some random flow of the air. And how the transition is done from laminar to turbulent flow is defined by a dimensionless quantity which is called as Reynold's number, Re. So this Re is defined as V into LF divided by Vk, where V is the characteristic velocity This is given in meter per second. And LF is the dimension of the flow. Dimension of the flow, which is given in meters. And Vk is the kinematic velocity, viscosity. These units are meter per second. So this is a dimensionless quantity. And the first part, that is in the numerator, basically tells about the inertial forces, and the quantity which is in the denominator is actually viscous forces or viscous forces. So sometimes inertial force will dominate, sometimes viscous force will dominate. So depending on the value of these forces, the Reynold number is defined. And the Reynold number is actually, if that number is Re is less than 10 to the 10 to the power 3, this is called less turbulent. Atmosphere is less turbulent. And if you have Re is greater than 10 to the power 5, it is high turbulence. So Re less than 10 to the power 3, viscous forces they dominate. When Reynold number is 10 to the power 4, inertial forces dominate, and the atmosphere is considered highly turbulent. And if you, just to get some idea, that near the ground, if I assume LF as 2 meter, which is the dimension of the flow, and wind velocity, let us assume as 1 meter per second square, 1 meter per second, then, and Vk, the value is 0.15 into 10 to the minus 4 meters square per second. And if you calculate the value of Reynold number, it comes out to be of the order of 10 raised to the power 5, which is near the surface, which means at this velocity, near the surface, the atmosphere is turbulent. Now, let us now try to understand why atmospheric turbulence will cause reduction in or increasing the bit error rate or the probability of error. So, as the signal which is getting received at the receiver is random, because you require minimum certain number of photons in order that the receiver should be able to detect the signal. Now, this is fluctuating. The number of photons which are arriving because of the turbulence, that is fluctuating. It's a random variable. So the probability of error actually depends on the signal strength. So PEA, let us define PEA, is the probability of error for the signal strength A. Now, the signal strength which is getting received as a PDF, which is defined by PA, because it is changing with time and turbulence is changing this parameter, so it has a PDF. So the property of this PE, the probability of error, basically is decided by two parameters. First one is what is the mean value of the probability of error, and the second moment, which is the variance in the probability of error. So the mean is defined as PEA, PA, that is the PDF of the received signal strength, and variance is PE minus ensemble average of PE whole square dA. Now, if I use a Taylor series for expanding PE around ensemble value of my received signal strength, PEA, I get this expression which is written here. that is PE2. This is a second derivative with respect to A, that is d square PE by dA square into ensemble average of the received signal, and theta A, this value is actually from 0 to 1. It can take any value from 0 to 1, and then the rest of the quantities. And if you see that PE, average PE, will always be greater than PE at some average signal strength, because this function is positive. Why this is positive? Because you have the second derivative of probability of error with respect to signal strength. So if you plot any typical curve, suppose this is signal strength or signal to noise ratio, and on this side you have the probability of error. It is a nonlinear curve with a positive second order differential. So because of this nature, this quantity is going to be, this quantity which I have is going to be positive. So my average probability is actually will change with the presence of turbulence in the atmosphere. So this atmospheric turbulence will have an effect on the performance of the link. It is going to degrade the probability of error. Now let us to understand the turbulence effect which is a laser beam will suffer. We need to model this, and the very important model which is used for modeling turbulence effect is Kolmogorov model or Kolmogorov theory. So in this theory, basically it explains about how the energy is transferred from large eddies to smaller eddies, how much energy is contained in the eddies, how much energy is converted into or dissipated into heat. So there are bigger eddies, there are smaller eddies, and those eddies, let us these are some smaller eddies, and these are some mid-size eddies in that one, and these are smaller eddies. And let us have the outer scale diameter for these bigger eddies is say L0, and for smaller eddy is say small L0. So this will be small L0. Now, the large size eddies, they are unstable, so they break into smaller eddies, and again these smaller eddies will further break down into further smaller eddies, and this process goes on until the Reynold number is small and eddy motion is stable in the atmosphere, and molecular viscosity is effective in dissipating the kinetic energy in the atmosphere. So basically what is happening here in this is there is an energy transfer happening. From bigger eddies to smaller eddies. So energy injection, this point can be energy injection, and in the end there is some dissipation. So this can be explained using energy cascade flow. So the energy from the bigger eddies, they are transferred to small, they break into smaller and then further smaller, unless you have a stable system or you have low Reynolds number, and then finally the energy is dissipated. Now this effect as per Kolmogorov is actually, follows a standard r raised to power 2, 3 power law. I'll explain this. What is this? So if I take two position vectors r1 and r2, which are separated by r, and this r is between the outer scale of eddy, that is L0, and smaller scale of eddy, that is L0. So this effect, follows a typical or standard. This has been proved experimentally as well. R is for 2, 3 power law. Now let us define a structure function, because ultimately we are modeling the turbulence effect in the atmosphere. So we need to define, because the temperature is changing, the refractive index in the atmosphere is changing, or it is different at different places. Velocity is different places. So let us define a typical standard function, structure function for a random variable xr, which is actually a function of r1 and r2, the two position vectors which I had mentioned here, separated by r as given here. And this is equal to xr1 minus xr2 mod square, and then the average is taken. So this is a definition of a structure function. Now xr will have two components. One is mean component, which is sort of average, and then you have the fluctuating component. So basically r can have some mean component, and then there is over it there is some fluctuating component. And if I denote this xr as the mean component and x prime r as the fluctuating part, and put this value in this expression and do some calculations, then I will get this structure function as given this. So where I have grouped the mean part, and then this is the fluctuating part. So this is the fluctuating part, and this is the mean part. Now we are able to understand the structure function of different quantities. Or for example, if I want to define the structure function of wind velocity, and as I mentioned that this is in the inertial range, because this 2/3 power law is actually valid in the inertial range, because there are two types of ranges, viscous range and inertial range, but this is valid when you are in the inertial range. So for the wind velocity, the structure function will be v1 minus v2, where v1 and v2 are the velocities at 2 points. In an earlier case, we had r1 and r2. So at those points separated by a distance r, which will be given by structure constant cv square, velocity structure constant. This is velocity structure constant, into r raised to power 2/3. This is that famous 2/3 power law under inertial range. And similarly, this can be done for temperature, where dt RT is equal to Ct square, and Ct square is temperature structure constant into r raised to power 2/3. So this is the variation of temperature at 2 points defined by r1 and r2 vectors. This is for velocity, and this is for temperature. And similarly, the refractive index is also changing from one position to another position. And let us assume that it has two parts. One is the constant part, which we will take as 1 for air, and then n dash, which is a fluctuating part. So this is 1 plus n dash r. And if I do some calculations, then this can be, because this is function of pressure and temperature, so this can be written as 1 plus 79 into 10 to the minus 6 P dash T divided by T dash T. And dnr n is defined by Cn square. This is refractive index structure constant into r raised to the power 2 by 3. So we have defined all the three quantities: the temperature, the velocity, and the refractive index. And using other equations or which have not been discussed here, so you can relate Cn square and Ct square using this formula. So Cn square and Ct square can be related. So now let us see the effect of turbulence, what actually happens because of turbulence. So the first effect which happens is beam wander. Now there are eddies which are small, which are size, and then you have a beam size. So if the eddy size is larger than the beam size, then the whole beam is actually deflected. And in the receiver, there's a possibility that you might miss the beam. So what happens actually, if this is a beam going in this direction, because of the eddy, it might get deflected. And your receiver is, for example, here. So you may miss the receiver. Ideally, you should have gone like this. So you will miss the receiver. The beam will miss the receiver. So this is called as beam wander. The other is scintillation. The eddies which are of similar size as the beam size, these eddies will act like a lens. So sometimes they will be focusing on the radiation, optical radiation, or sometimes it will defocus. So because of this focus and defocus, there will be some, you will have some constructive and destructive kind of pattern onto the receiver. And if you see in the plane of the receiver, you will get some dark spots, some bright spots. This is also called as speckle pattern. So this will result, this is what is called as beam scintillation, and it is because of the eddies which are of similar size as the beam size. So there are ways of handling, these anomalies, and how do you mitigate this effect, that we will discuss later. So this is the another effect which turbulence atmosphere will have, that is a beam scintillation. The third is beam spreading. This is because of the eddies which are smaller than the beam size. So what happens, because of these eddies, the beam will get scattered. There will be redistribution of energy in the wavefront. So, and because of these redistribution of energy, because of this scattering, there will be loss. The light will get, or the laser beam, the power will get spread over a large area, and on the receiver you will get much less area. So this is called as beam spreading. So basically what happens, if your receiver size is this much and beam has, for example, spread this much, so only part of the energy is captured by the receiving area. So the turbulence, the atmospheric turbulence, has these three effects, and we will study in detail about these effects. So let us start with the beam wander. So in beam wander, what happens when the laser beam travels through the atmosphere, the hot spot where the energy is maximum actually keeps changing. There is a snake-like movement. So sometimes hot spot is here, sometimes the hot spot is here, sometimes this is here. And if I see the profile, for example, corresponding to this hot spot, it will be something like this is a Gaussian beam, we're having maximum at this point, and this will give me a maximum at this point. This will give me maximum at this point. So if you see the overall effect, there will be a Gaussian, spread out Gaussian, or the Gaussian profile is skewed. So this is what you get at the receiver. So this is actually the movement of hotspots as the beam travels in the atmosphere. This happens because of the turbulence. So the other effect it can have is, there'll be beam wander. So if I make a model, try to model this beam wander. So basically, this is one effect which will happen because of the movement of the hotspot. And also another issue will be that when you have, for example, say these are, say, so this is, say, let me redraw this. So what happens, this is a center of this circle. These are the small hotspots where, let me denote this as, the beam width size here is omega short term, and because it is changing, so it will ultimately result in a bigger circle of this radius, and let me denote this as a omega long term. So the beam size, this is a short term because of the hotspots, and then the combined effect of this hotspot and the centroid moving of the beam will result in a bigger circle which will have a radius of omega LT, or this is omega long term, and this is actually the beam wander. So this will have some average value, RC square. So this is the beam wander effect. So what actually, if I try to model a beam wander, so this is the long-term beam width at a distance r. This is long-term beam width at a distance r, which is happening because of the turbulence. And this beam width omega square r is actually because of the space, because the wave is traveling through the space, and the space will increase the beam width at a distance r, which is given by w square r. And this particular component is because of the short, small size eddies, and this is because of the large size eddies. This width increase is because of large size eddies. And this is the beam wander part which I had explained. So you can say this part whole is short term, that is short term. So basically it gives you RC square half will be omega square LT R minus width W square, this is W, R and this is short term. Or you can write this as and this is the beam wander. So beam wander can be written as this. So let me again explain this. So you have hotspot moving, and also the centroid of the beam is also moving around its central position, and because of this, the long-term effect will be a bigger, hot beam size or spot size of dimension WLT, and this WST is for the smaller because of the hot spots, and then this gives you the beam wander part, which is and the whole beam wander model can be modeled by this equation. And the overall effect of this beam wander model will be, if you launch a Gaussian pulse like this, then because of this beam wander at a distance r, the pulse will become flattened in the middle. So near the bore site, it will get flattened. So this is the... So if you see the power in this range, it has actually decreased. So it has introduced some sort of pointing error in the system, which is, you can say this can be defined as the rho sigma or rho PE pointing error. So because the beam has flattened, you have less power, and also it is less power across this whole width. So effectively, the system has a pointing error introduced into this because of the turbulence effect. So this is the effect which the beam wander will have.